Okay, so let us look at this page now. Hydrolysis of alkyl halide. So what is alkyl halide? Alkyl halide is actually halogenoalkane, which is the AS organic, halogenoalkane. So they are trying to give us a mechanism. Primary alkyl halide mechanism. So if you remember primary halogenoalkane, they are going through primary halogenoalkane. Primary halogenoalkane, SN2. SN2, okay, SN2. If you remember something like that. Tertiary halogenoalkane, SN1. SN1 one reactant. So primary halogenoalkane, SN2. Two reactants. Okay, two reactants. So let's see the mechanism here. This is SN2 mechanism. SN2. These are SN1 mechanisms. Okay, now let's see. First steps, the halogenoalkane, which is the bromopropane. No, it's butane, bromobutane, 4 hydrogen. Sorry, 4 carbon. Bromobutane react with hydroxide ions in aqueous. Then they form a pentavalent. Okay, pentavalent transitions species. Okay, so temporarily one, and then they quickly kick out the Br, and then they form to butanol, and the bromide come out. So this is the slow step, and this is the fast one. Okay, so the slow step is to form the pentavalent transitions species. So it takes time, it's slow, and these slow steps is rate determining steps, and hence the rate equation is K, this thing of first order, because here 1, and this thing hydroxide first order also. So like what we discussed before, the slow steps will determine the order. Okay. Now let's see tertiary alkyl halide mechanism, which is SN1. So this is tertiary halogenoalkane. SN1 means start from one reactant. So this one reactant will kick out the bromides on its own. Okay, kick out the bromides. And then it form a carbocation ions. And this quickly react with the hydroxides and quickly form alcohol, tertiary alcohol, plus bromide. So this is fast. If you look at the equation, bromide should not be here. Bromide should not be here. Okay, let's say I just cut away the bromide. Okay, so the second step is fast. And rate determining step is the first one. The first steps. The first mechanism here is rate determining steps. And the rate equation is coming from the rate determining step, the reactant itself. So K, concentration of this, power 1. Okay, now let us move on. One quick example again. Constructing rate equation for multi-steps reactions. The mechanisms for the productions of NO2F involve 3 of these steps. Now, A, what is the overall stoichiometric equation? So that means overall equation. So let's find out what is the same thing on both sides of the equation. So first we have this thing, the NF2 and NF2. So we can cut away NF2 because it happened on different side of the equation. NF also we can cut away. O2 we can cut away also because at different sides. Okay, now let's cut away NF2, NF, and O2. So after doing so, the overall will be NO2, we have 2 of them, and F2. On the right, we have 2 NO2 F. Okay, so B, rate equation. R equal to, we look at the slow steps, which is the rate determining steps. We have K. We follow the reactant in the slow determining step. We have NO2, first order. Then we have F2, first order also. So we get the equation, the rate equation. Okay, so settle on this page. So we have done the main, the most important concept of this chapter. Determine the order of the rate equation. So what we have now is just something that is theory, yeah. Okay, theory. We can go through this quickly. 4.7, measuring reaction rates. So there are many ways to do so. Okay, so you want to measure rate. So for example, you can measure the rates by measuring the volume produced, the volume of gas produced. You can measure the volume, or you can measure the rate by checking how fast the color change. So that is one way. Okay, so or you can measure the rate by checking how fast the mass decreases or how fast the mass increases. That is another way also. There are so many ways to determine the rate. Okay, so now let's see the notes. Sampling. Method that involve taking small sample of a reaction mixtures at various times and then carrying out chemical analysis on sample. Okay, so which means, let's say, imagine you have a lot of reactant here that react and form product. So at every 5 minutes, let's say, you take out some sample. So you take out some sample, and then after that, you can check concentration, for example. Every 5 minutes, you take out a little bit of sample and check their concentration. How to check concentration? For example, you do titration to check concentration. That is an example. So every 5 minutes, you take a sample and check concentrations, and then you work out the rate, work out the rate. Take the concentration divided by time, for example. Okay, now let's see here. Again, method that involve taking small sample of a reaction mixtures at various times, like every 5 minutes, and then carrying out chemical analysis, for example, titrations. Do titration to find the concentration on sample. Chemical analysis. What kind of chemical analysis? For example, do titration, right? What I said is, okay, let's say what they do here. C4H9Br. Okay, again, this is bromobutane plus OH minus. So this is a halogenol alkane. React with hydroxides. So this is what we call the SN2, the SN2 mechanism. Okay, now they form butanol plus bromide. This is the overall equation. If you compare to just now they give mechanism. So where it is here, this one change to the pentavalent, and then the pentavalent change to the product. They give mechanism. Now over here they give overall. This is the overall equation. Okay, the overall equation is given here. So they said sample remove. Samples remove at various times. Samples. So samples remove at various times and quench. Stopping or slowing down reaction. Example, cooling in ice. So when you take out the sample, right, we don't want the bromobutane to react with OH minus anymore. So what we do is we put them in ice. So let's say in ice water. So when it's cold enough, reaction stops. So after that, next point, hydroxide concentration can be found using titration. You know, the hydroxide concentration keep decreasing because it react to form product. So because of that, it react to form product. So the concentration of OH minus keep decreasing. So let's say this is the initial one. This is after 5 minutes. This is after another 5 minutes. So you take each of the sample to do titration to check the amount of hydroxides. Then you plot graph and calculate rates of reaction. So you can plot graph. So what kind of graph you can use? Just now on the first page, you have two types of graph. So you can use those graph to determine. Okay, you can use those graph to determine the rates of reactions. So you can do calculation at the end. So now let's move on. Continuous method that involve monitoring a physical property over a period of time. So that means, for example, you can, let's say again, you have a container that's the chemicals react here. So you can just check, for example, the change in volume of gas produced. Okay, so which is like, something like this. Okay, I draw out the apparatus. Conical flask. This is the inverted burette. Okay, so we can do something like this. We set up the apparatus in this way. Okay, your reactant is here. The gas come out to the other side. Okay, so this is one example for our case here. You can see they use magnesium plus HCl. So you can put some magnesium. Here. Magnesium. You can put HCl. Okay, so the continuous method here is like, let's say every 3 minutes or every 2 minutes, or maybe 1 minute should be fine also. So it depends on how much concentration you are using. So every 1 minute or every 30 seconds, you look at the volume of gas. Okay, no need to do sampling. Sampling is like a bit slow. You quickly look at the volume. If you're not fast enough, you record in your video cam. Record in your video cam and you read again. You pause the video. And read again the volume of the gas. Okay, so the gas keep coming here. Okay, you see they found magnesium chloride and H2, right? So the gas keep coming here. Instead of taking sampling, and we just read the volume of gas straight away. Okay, that is continuous. Measure change in volume of gas using a gas syringe. That is one way, gas syringe. Or use the inverted burette like what I show you. Take down reading at regular interval. Plot graph and calculate rates of reactions. Okay, so same situation. You can plot, let's say you can plot concentration versus time for the first case. Okay, for the first case, you can plot concentration versus time. The gradient is the rate. The second case, you can put volume versus time. Okay, let me draw out. Okay, the first case here, you can put concentration versus time. Concentration of hydroxide versus time. Okay. The second one, you can plot volume of hydrogen gas versus time. And then from here, you count the rate. Rate is just the gradient. Okay, rate is the gradient of the graph. Now, next one, changes in color. Changes in color is also counted under continuous method. So meaning that you can see the example here. CH3, CO, CH3. This is ketone. Ketone, this is propanon. Propanon, plus iodine. Plus iodine become CH3CO, CH2I plus HI. Okay, so it seems like in AS we don't learn something like this. What I expect here is this is like a free radical substitution because it happens to the CH3, CH3. Yeah? So CH3 is something similar to alkane. So the alkane have free radical substitution happen and then it become I. Okay, but we don't want to focus on that actually. So we focus on the I2 here is brown color. So at the end when the I2 changes to I here and HI, so you should expect the brown color fade. Okay, fade. Okay, so from brown then to orange to yellow then to colorless at the end. So HI and this product has no color. So it changes color and we use colorimeter to measure the color. To measure the color, the intensity. So measure the amount of light absorbed as it passes through solution, recorded as absorbance. You use absorbance. Absorbance versus time your graph. So you see the diagram here. Okay, so you take a light source which produce white light passing through the filter, and you have colored lights come out. If your filter is blue, then blue light come out, and then the blue light strike the container, the tube, test tube with sample. Okay, so your test tube with sample is of certain either brown, orange, or yellow depends on which stage are you or even colorless. Then they come through, they pass through the tube, the test tube, and at the end enter the colorimeter. So the colorimeter will give you the absorbance. Then you plot the graph. So more information here. They say before experiment, creates calibration curve by finding absorbance of different concentration I2 and plot a graph of concentration against absorbance. That means before experiment, right? You don't take these two react straight away, Like for example, you take 1 mole of I2, you let it pass through. You see how much absorbance is obtained. Then you put 0.8 mole per dnq. You put here. Then you see the absorbance. Then you put 0.6. You put here. Then you put 0.4 mole per dnq. Then you put here. And that is what we call the reference graph or the calibration curve. Okay. So after you have the information ready, then you let them react. Then you put here. Then you keep record down the absorbance at different time, and then you compare with the calibration curve to know the concentrations of I2 at that moment. Okay, so during experiment, measure absorbance from meter at regular interval. Maybe every 1 minute you look at the absorbance. From the absorbance value, you compare with the calibration curve, then you know the concentrations of I2 remains. And use calibration curve to convert values into concentration. So you get concentration at the end. Okay, but you need to create the calibration curve beforehand. So that is a bit troublesome.